A single map can break how we see the cosmos. For centuries, the biggest leaps in astronomy weren't from looking through a telescope. They came from making a chart. This is about 25 maps that changed astronomy. By the end, you'll see the night sky differently, not as random lights, but as a story, a structured story that's still being written. How did dots on ancient clay redefine time? What hidden structure in empty space made us rewrite the universe's blueprint? And what's waiting to be found on the next great map? That shift from a chart to something that changes everything, it's a particular kind of magic. It's when a map stops just showing where things are and starts to tell you what they mean. A map that really changes things gives you a new language for the universe. It's not just putting more dots on the page. It's connecting those dots so you see a pattern nobody noticed, a structure that was always there, just hidden. And a lot of the time, that needs a leap in technology. The telescope, it didn't just give us better maps of the moon. It broke the old idea that the heavens were perfect, because now we could see mountains on the moon, spots on the sun. Then centuries later, a satellite looking into the dark of space catches this faint, even glow, the afterglow of the Big Bang. That map becomes the baby picture of the universe. But it's not just technology. Sometimes the revolution is a new idea, a framework so powerful it makes you redraw everything. A scientist looking at a plain chart of star positions might realize the data is whispering a secret, that the stars are moving in a way that shows something massive and invisible is there, rewriting gravity itself. These maps become landmarks. They're the reference points everyone uses after. They don't just answer old questions. They build a whole new foundation, a bedrock where you can ask stranger, better questions. In the end, a revolutionary map is an argument. It's a thesis written in the positions of galaxies, in the wrinkles of ancient light, in the geometry of empty space. And its goal is to convince you that everything you knew was just one page in a much larger story. That need to observe the universe started with something basic. We had to know what was out there first. We needed a list, and the first things on that list weren't written by scientists. They were made by storytellers, by farmers, by sailors just looking up. The night sky was this huge moving pattern of light, and the mind looks for shapes, so we connected the bright points. A hunter, a bear, a scorpion, those constellations were the first maps. Not on paper, but in the memory of cultures everywhere. They were practical. They marked the seasons. They told you when to plant, when to harvest. They guided ships across open water. But they were also myth. The stars told stories, gods and heroes, great beasts, long journeys. A language of light anyone could read. That was the first big shift. The sky stopped being just a place of spirits. It became a system you could name, you could track it, you could use it. The Babylonians pushed that further. About 3,000 years ago, their scholars started writing down the motions of planets and stars on clay tablets. This wasn't storytelling anymore. This was data. They made the first star catalogs, lists of objects and their positions. They could predict lunar eclipses. They followed the wandering paths of planets against the fixed stars. They were building a reference library for the sky, proving its behavior wasn't random. It followed rules you could write down. Later, in the Islamic Golden Age, that craft of measurement became an art. The astrolabe, this intricate brass device engraved with coordinates, it was a portable model of the universe. You held it in your hand, line it up with the horizon and a known star, and a traveler could tell the time. Find their latitude, find the direction to Mecca. It was a physical map, a computer for its time. It translated the abstract clockwork of the heavens into practical guidance on the ground. All those early efforts, the myths, the catalogs, the astrolabes, they did one monumental thing. they laid a grid of human understanding over the celestial unknown. They created a fixed inventory, a stable backdrop, and by doing that, they gave astronomers the most essential tool, a baseline. Once you have a detailed map of what should be stationary, you can finally see what moves. You can measure change, you can spot the anomaly. Every revolutionary map that came after, charts of comet paths, plots of receding galaxies, all relied on that simple, ancient principle first etched in clay. The universe had been catalogued, now the real detective work could start. The first great map that changed astronomy was written in clay. It wasn't a picture. It was a list, a set of Babylonian tablets called MUL.APIN. They're over 3,000 years old. This was a manual for the cosmos. It named constellations. It tracked the paths of the sun and the moon and the planets. It laid out a calendar based on when certain stars first appeared at dawn. Its purpose was practical. It told farmers when to sow seeds and when to harvest. It guided the timing of religious ceremonies. It connected celestial events to omens, reading the movements of the heavens as messages about the fate of kingdoms. But beneath that tradition, something more revolutionary was taking shape. This was a shift from telling stories about the stars to systematically recording their behavior. The map was a data table. It turned the sky from a realm of myth into a system you could measure. You could predict it, you could use it. By creating this fixed reference, this early catalog established a foundation. For the first time, someone could note an anomaly, a new star where none belonged, a planet straying from its predicted path. They could see it because they had a record of what was supposed to be there. That principle, born on those tablets, is the same one that drives our most advanced sky surveys now. Every modern telescope scanning for asteroids or exploding stars or distant galaxies is continuing the work those Babylonian scholars started. They gave us the first rule of cosmic discovery. To find what is new, you have to first know what is old. The next one was made for an empire. This was centuries later in Alexandria. A scholar there, Claudius Ptolemy, was putting together a masterwork. It was called the Almagest, the greatest compilation, and for more than 1,000 years, that's what it was. Ptolemy wanted to map the whole known cosmos with mathematical certainty. He catalogued over 1,000 stars. He gave each one a precise position. He used a coordinate system, celestial longitude and latitude. But he didn't just list them, he put them inside a grand model of the universe, a cosmic mechanism, with the Earth fixed right at the center. The planets moved on complex circles. Circles within circles, their paths were calculated to match centuries of observations. That was the map's real power. It wasn't a static picture, it was a predictive engine. You could use Ptolemy's equations, his star chart, to forecast where Mars would be in 6 months, or when the next lunar eclipse would happen. The accuracy was stunning. The revolutionary core of the Almagest, later on, it wasn't the Earth-centered idea. Many cultures had that. It was the synthesis. Ptolemy fused observation with geometry. He created a reproducible mathematical language for the heavens. Anyone, anywhere could use his system and get the same results. That reliability made it the definitive textbook. For 1,500 years, it guided navigators, it informed calendars, it shaped the cosmology of entire civilizations. Medieval Europe, the Islamic Golden Age, where scholars refined its tables further. The map was so effective at predicting what people saw that its fundamental error, placing Earth at the center, became almost impossible to question. The Almagest proved a truth. A profound and dangerous one. A map can be brilliantly, usefully wrong. Its mathematical elegance described the sky's motion so perfectly that it concealed a deeper reality. It would take a revolution, not of observation but of imagination, to draw a new map with the sun at its heart. The map that would challenge Ptolemy's world had been sitting in a cave for 1,000 years. In 1900, a Taoist monk named Wang Yuanlu was clearing sand from a sealed chamber in the Mogao caves near Dunhuang. He wasn't looking for stars. He was just tending to a forgotten Buddhist library, but inside, among tens of thousands of manuscripts, he found one scroll. It was drawn on paper around the year 700 during the Tang dynasty. It's the oldest complete star atlas we have, and it wasn't a list, it was a picture, a graphical map of the whole night sky. The Dunhuang Star Atlas is a masterpiece. It charts more than 1,300 stars. They're grouped into 257 Chinese constellations. The lines between the stars aren't just decoration. They're precise. They show the shapes of celestial officials, mythical animals, palaces, the whole Chinese cosmic bureaucracy. Its significance is profound. It works on two levels. First, it's a monumental achievement from a parallel tradition. While scholars in the Mediterranean were refining Ptolemy's system, Chinese astronomers were making their own sophisticated charts. They had their own coordinate systems, their own methods for predicting eclipses, their own celestial mythology. This map proves the drive to chart the cosmos is a human universal. It didn't come from just one culture. Second, and maybe more powerful for modern science, this map is a time capsule. It's a snapshot of the sky on a specific night. Seen from a specific latitude over 13 centuries ago, that gives astronomers a fixed point of comparison. By placing the stars exactly where they were in the year 700, the atlas provides a baseline. So when we compare those ancient positions to where the stars are now, we can measure their tiny, creeping motions, their proper motion, the real movement of stars through the galaxy. Over a few human generations, that motion is invisible, but over 1,300 years it becomes measurable. This ancient map, drawn by hand on paper, lets us witness the slow dance of the galaxy. It turns art into data, history into a scientific instrument. The monk who found it uncovered more than a relic. He found a clock for the stars, precision turned into a weapon. There was this Danish nobleman, Tycho Brahe, in the late 1500s. He built an observatory on an island, Uraniborg, and he was fighting a quiet war against the cosmos. His goal wasn't to imagine a better model. It was to measure it, to pin it down. He built these instruments, massive brass quadrants and sextants. Some were over 6 feet across. Their arcs were finely engraved. He had no telescope. He relied on pure mechanical sight. He'd stare for hours, aligning a star with a tiny pinhole sight, then reading its position from the graduated metal arc. His obsession was data, unprecedented data, meticulous, relentless. The result was a star catalogue, 777 precise positions. His measurements were accurate to less than 1 arc minute. To understand that, hold your hand at arm's length. The width of your little fingernail covers about 1 arc minute of sky. He was measuring pinpricks of light with that level of fidelity. Night after night for decades, it was the most accurate map of the heavens ever made by human eye and hand, and that precision became a bomb. It exposed tiny discrepancies in the old models. The planets, especially Mars, didn't move according to Ptolemy's perfect circles, or even Copernicus's sun-centered model. The data was off just by a little. But Tycho's map was so good, so trusted, that the error couldn't be ignored. It was a crack in the celestial machinery. After Tycho died, this treasure trove of numbers went to his assistant, Johannes Kepler, a brilliant mathematician. Kepler inherited the data and the problem. For years he wrestled with Mars's orbit, trying to fit it into circular paths. It wouldn't work. Tycho's map refused to be lied to. In his frustration, Kepler was forced to consider a heretical shape, an ellipse. The moment he tried it, the numbers snapped into place. The planets, including Earth, moved in elliptical orbits with the Sun at one focus. The revolution wasn't the telescope, it was the ruler. Tycho Brahe's map proved the universe could be interrogated with numbers. That a radical improvement in the quality of data, the sheer faithfulness of the map, could shatter a belief system that had stood for over a millennium. He gave Kepler the ammunition to rewrite the laws of motion. From that point on, astronomy wasn't about preserving philosophical ideals of perfection. It became a science driven by measurement, where the map's accuracy dictated the theory, not the other way around. Galileo Galilei published a book in March of 1610. Sidereus Nuncius, the Starry Messenger. It had engravings, drawings of the moon, but they were different. He'd looked through his improved telescope. And he saw a world, not a perfect, smooth sphere. He saw mountains, valleys, shadows. He sketched the Terminator, that line between day and night on the moon. The long shadows showed a rough terrain like Earth. He included a diagram, Jupiter, with 4 small stars lined up next to it. He tracked them night after night. They weren't background stars, they were moons orbiting Jupiter, and he described the Milky Way, not a cloud, a vast collection of stars, countless suns. This book was a visual argument, a manifesto. For 2,000 years the view was different. Aristotle's view, the doctrine, the heavens were perfect. Unchanging, celestial bodies were made of a special substance, smooth, eternal. Galileo's maps destroyed that. Here was direct evidence. The moon had mountains you could measure. Jupiter had its own system. The fixed stars weren't all pinned to one sphere. The cosmos was textured, dynamic. It was made of places. This shift was philosophical. It moved humanity. We were no longer at the center of a perfect, finite cosmos. We were on a rocky planet, circling a star, in a universe of immense complexity. The map changed the question. It was no longer about how the perfect heavens move around us. The new question was, what are these other worlds like? If the moon is a world, could it have life? Could Jupiter? The telescope became an engine of discovery because Galileo used it to make a map. He gave the public eyes to see. And once you see the craters on the moon, you can't see it as a perfect pearl again. The universe had become a neighborhood. A single drawing of a rocky landscape opened the door. Galileo had already proven the moon was a world, so the next step was to map it. In 1647, a brewer and counselor from Danzig published a book that did that. Johannes Hevelius, he called it Selenographia, the description of the moon. It was a massive work, the first real lunar atlas. Hevelius spent years up on his rooftop observatory, sketching the moon night after night, phase by phase, through his long telescopes. The engravings he produced were stunning. They showed the moon in incredible detail. Craters, mountains, plains, all drawn with an artist's eye, but also a surveyor's precision. He gave names to these features. Mountain ranges he named after earthly ones, like the Alps and the Apennines. Craters he named after philosophers and scientists. But his most important work was mapping the libration zones. The moon doesn't show us the exact same face all the time. It wobbles, it rocks back and forth, so over time we get to peek a little around its edges. Hevelius carefully charted these marginal regions, these glimpses of the lunar limb. He was mapping the boundary of the known. That was the shift. Hevelius wasn't just drawing what he saw. He was applying the full discipline of map-making to another world. He used grids, he measured angles, he established coordinates. He treated the moon not as a light in the sky, but as a landscape. A place, and by doing that, he established selenography as a real science, a branch of geography just off the planet that set the standard for everything that came after. When we later mapped the deserts of Mars, or the clouds of Venus, or the plains of Pluto, we were following the blueprint Hevelius made. He taught us to see other worlds not as dots of light, but as destinations. Real, solid places waiting to be explored. His atlas was a passport, and it stamped the moon as the first stop on a journey that's still going. The map that guided an empire started with a shipwreck. Late in the 1600s, a fleet of English warships was sailing the Channel. They misjudged their position. they ran onto the rocks of the Isles of Scilly. Nearly 2,000 sailors died. The cause was faulty navigation. The charts of the stars were wrong, so King Charles II founded the Royal Observatory at Greenwich. He gave the first astronomer royal, John Flamsteed, a direct order: map the heavens with enough precision that English ships would never be lost. Flamsteed's life's work was the Historia Coelestis Britannica, a catalogue of over 3,000 stars. He used telescopic sights on his instruments that gave him far greater accuracy than Tycho Brahe's naked eye methods. Night after cold night, he recorded positions. This wasn't about finding new worlds. It wasn't about cosmic laws. It was a survey, a geodetic project for the sky. The map's immediate value was immense. It became the backbone of maritime navigation for the British Empire. The stars became reliable signposts for global trade and naval power. But the deeper revolution was invisible. This was the first major star catalogue not made by a lone scholar in a private observatory. It was made by a state-funded institution. The map represented a shift. Astronomy was becoming an organized national enterprise. The state invested in precision for practical ends like navigation, but also for the scientific authority it gave them. The stars became national infrastructure. Flamsteed's catalogue was published after his death in 1725. It signaled that mapping the cosmos was no longer just the passion of individuals. It was the systematic work of institutions, a collaboration between science and state. That collaboration would define the next 3 centuries of discovery. The telescope had shown us new worlds. Now, the institution would give us the means to chart them all. The star catalogues were tools of empire, but William Herschel saw them differently. He was a musician, and he became obsessed with the stars. He built his own telescopes, the largest ones, the finest ones in the world, and he started a project of staggering ambition. He decided to count the stars, all of them, not just the bright ones. He called it star gauging. He would point his telescope at a patch of sky, and he would count every point of light. Then he'd move to another patch and another. He did this over 600 times, sweeping the heavens methodically. He wasn't just making a list, he was taking a survey, a demographic study of the cosmos. All those thousands of hours at the eyepiece led him somewhere, to a revolutionary conclusion. He published a diagram in 1785. It was a cross-section of the Milky Way. The map showed our galaxy not as a band of mist but as a flattened disk of stars, like a grindstone, and the sun was positioned prominently near its center. This was the first scientific map, a map of the large-scale structure of our cosmic home. It was a leap of imagination, profound. Herschel had moved astronomy from mapping individual objects, planets, moons, stars, to mapping the architecture of the system itself. He asked a new kind of question. Not where is a particular star, but what is the shape of the place where all stars lie. Now his map was wrong in its details. He had no way of knowing about interstellar dust, vast clouds that block the light of more distant stars. His gauges were biased. They made the galaxy seem smaller. They placed us far too centrally, but the conceptual victory was absolute. He proved the Milky Way had a shape, a structure that could be measured and drawn. He gave us the first rough blueprint of our island universe, and that blueprint forced a new line of inquiry. If we live inside a disk of stars, what does that disk look like from the outside? Are there other such disks? The quest to map our galaxy's true spiral arms, to find other galaxies beyond it, that began with Herschel's simple act, the profound act of counting. He taught us to see the forest, not just the trees. The astronomer's hand couldn't keep up with the eye. For centuries, mapping the stars meant long nights at the eyepiece. You'd squint, estimate a position, then dip a pen to paper. Every chart was a translation, a human interpretation of light. Then the photographic plate arrived. In the late 19th century, observatories began pointing cameras at the sky, not just telescopes. A new project started, an ambitious name, the Carte du Ciel. The map of the sky, its goal was to photograph the entire heavens, to create a permanent record, an objective one. That was the shift. The mapmaker wasn't an artist or a scribe anymore. It was a chemical reaction, silver salts on glass, darkened by starlight over hours. That process removed the observer from the recording. It erased human bias. Fatigue, the limits of perception. A photograph didn't just show where a star was. It captured the exact intensity of its light, the precise pattern of its neighbors. A single, unblinking moment frozen in time, and it created a time capsule. A plate exposed in 1890 could be placed next to one from 1910. And in that comparison, in the subtle differences between two sheets of glass, the universe began to reveal its secrets. You could search for objects that moved or changed. A tiny point of light that had shifted position between the two plates, that was an asteroid, a new world in our solar system, a faint smudge on the newer plate, invisible on the old. That could be a distant galaxy or a variable star, its brightness slowly pulsing. The Photographic Sky Survey turned astronomy into a forensic science. It gave researchers the ability to rewind the sky, to compare then and now with perfect fidelity. This permanent record became the ultimate witness. Discoveries could be made decades after the original observer had passed. The universe was no longer just being observed. It was being documented with a patience and impartiality that human eyes could never achieve. Harlow Shapley needed a way to measure things in space. He wasn't looking at the Milky Way's disk itself. He looked at these swarms of stars orbiting it, globular clusters, dense balls of ancient stars held by gravity. They were like distant lighthouses, and inside them was a certain kind of star, a Cepheid variable. These stars pulse, they have a rhythm, and that rhythm tells you how bright the star actually is. Know the rhythm, you know the true brightness. Then you see how dim it looks from here, and you can figure out the distance. That was his ruler. He measured the distances to many of these clusters. Then he plotted them on a three-dimensional map. The pattern wasn't random. The clusters formed a huge spherical halo, and the center of that halo was a point far away in Sagittarius. The sun wasn't at the center of this system. We were in the suburbs, a quiet spot about halfway out from a dense, distant core. It was another Copernican shift. Copernicus moved us from the center of the solar system. Now Shapley's map moved us from the center of the galaxy. A demotion, a reorientation. His map did more than that. It showed the true scale. By measuring to those outposts, he found the Milky Way was about 300,000 light-years across, 10 times bigger than anyone thought. A vast island with us in an outer spiral. Later, the size estimate was corrected, made smaller, but his central insight was right. He had found the direction to the galaxy's heart. That core in Sagittarius, he gave us our first real cosmic address, not just a street but the city and the neighborhood. We weren't at the capital, we were out in the residential districts. And that changed the question. If we aren't central here, what else aren't we central to? The early 20th century had these long exposure photographs. They showed these faint smudges in the telescope, these nebulae. Some were spirals like pinwheels, others were smooth ellipses or just formless blobs. But the problem was identity. Were they clouds inside our own Milky Way, or were they separate universes, islands of stars far beyond? That was the great debate. And it raged without a clear answer. Then Edwin Hubble, using the new 100-inch telescope at Mount Wilson, he found a Cepheid variable star in the Andromeda Nebula. That measurement proved it was a separate galaxy, millions of light-years away, so the universe had just grown immensely larger. It was filled with these island universes. But then came a new challenge. With thousands of galaxies now confirmed, the sky was this chaotic menagerie of shapes. How do you make sense of it all? Hubble's genius was in the sorting. In 1926, he published this simple diagram. It looked like a tuning fork. On the handle were the elliptical galaxies. Smooth, featureless, labeled from E0 to E7, based on how round or flattened they were. Then the fork split. One prong held the spiral galaxies with a central bar of stars. The other prong held the ordinary spirals without a bar, and each prong was ordered further by how tightly wound the spiral arms were and by the size of the central bulge. It was a map of morphology, a classification system based purely on shape. That was the conceptual revolution. The tuning fork diagram gave astronomers a common language. Instead of calling something a faint, messy spiral thing, you could call it an SBC type, a barred spiral with loosely wound arms, and suddenly properties could be correlated. Ellipticals tended to be redder with older stars and little gas. Spirals were bluer with active star formation in their arms. The map also suggested a story. An evolutionary sequence. Maybe galaxies started as formless ellipticals and evolved into majestic spirals, or maybe they moved the other way. Hubble himself was cautious about that interpretation. But the diagram invited the question. It provided a framework, a filing system for the cosmos. Every new galaxy discovered could be placed on the map. Its shape told you something about its history, its composition, its inner life. By turning faint smudges into categorized families, Hubble's tuning fork did more than organize. It made the vast external universe feel knowable. It was a periodic table for galaxies, and just like Mendeleev's table predicted missing elements, Hubble's scheme hinted at relationships. Transformations that would drive astrophysics for the next century. He gave us our first field guide to the islands in the cosmic ocean. Measuring the distance to a star is a hard problem. You can see how bright it looks, but that doesn't tell you how far away it is. A faint star could be dim and close, or it could be incredibly bright and just impossibly far. And without a way to solve that, the universe was just a flat canvas, a collection of points with no depth. The breakthrough was a kind of map, not a map of the sky, but a map of the method. A conceptual chart, we call it the cosmic distance ladder. It's like a toolkit. Each tool works for a certain range, and each one helps you set up the next. The first step is the simplest, and it uses a trick your eyes already know. Parallax. You hold up your finger, close one eye, then switch. Your finger seems to jump. That shift, measured with extreme precision against the background stars, gives us the distance to nearby stars. It's a geometric fact, a direct triangulation from Earth's orbit. But it only works for stars within a few thousand light-years. Beyond that, the shift is too small to see. So astronomers needed another step, and they found it in a certain kind of star that pulses. Cepheid variables. These stars brighten and dim on a regular schedule, and the key was this: the period of the pulse tells you the star's true brightness. A slow pulse means the star is genuinely brilliant. A fast pulse means it's fainter. So you find a cepheid in a distant cluster. You measure its pulse rate to learn its true wattage. Then you see how dim it looks from here. The gap between how bright it is and how bright it appears gives you the distance. That step extended our reach from thousands to millions of light years. But to reach across billions of light years to the farthest galaxies, we needed something brighter that came from a specific kind of explosion, a type Ia supernova. This happens when a white dwarf star steals too much material from a companion. It crosses a critical mass and detonates. Because the trigger mass is always nearly the same, the explosion's peak brightness is always nearly the same. It becomes a standard candle of staggering power. It can outshine an entire galaxy. See one in a distant galaxy, measure its peak, and you can calculate the distance to that galaxy. This ladder, parallax, cepheids, supernova, it's a map of cross-checked confidence. Each step is calibrated by the one below. Parallax measures near by cepheids. Those Cepheids, now understood, measure distances to galaxies that have supernova, and those supernova measure the farthest reaches. This meta-map of method did more than give us numbers. It gave us a verified framework. It made the vastness quantifiable, and with that quantified vastness, Edwin Hubble made his next discovery. By measuring galaxy distances and combining them with their redshifts, he saw the pattern. The universe wasn't static, it was stretching. Every galaxy was rushing away. The distance ladder provided the yardstick that revealed the expansion of the universe itself. It turned the cosmos from a static stage into something dynamic. The map of how we measure became the key to mapping everything else. There was this hiss. It kept showing up in their data. Arno Penzias and Robert Wilson at Bell Labs, they had this big horn antenna. They were trying to map radio signals from the galaxy. But this static was everywhere, every direction, all the time. They went through everything. They cleaned the antenna. They got rid of some pigeons. The noise was still there. It wasn't the equipment. It wasn't from the ground. It was coming from the sky. And it wasn't just noise. It was a signal, a kind of whisper. What they found was the cosmic microwave background. The afterglow from the Big Bang. Their map wasn't a picture. It was a chart, a plot of intensity, and it was the same in every direction, a uniform sea of microwaves filling everything. That simplicity was the point. It was the first direct evidence for the Big Bang. If the universe started hot and dense and then expanded and cooled, the math said there should be a cold remnant left over. A faint glow, and they had just measured its temperature, about 3 degrees above absolute zero. That chart of static was a baby picture of the universe. From when it was 380,000 years old. Before this, the debate was theoretical. Big Bang versus steady state. Now there was proof. A fossil radiation field everywhere in space. This map gave cosmology a foundation, a starting point. The universe had a documented birth, and this background was the canvas. A smooth, uniform fabric, and all the structure we see now, the galaxies and clusters, they would form later, as tiny ripples in that early sea. That faint hiss in New Jersey wasn't interference. It was the echo of creation, a map that doesn't show where things are in space. It shows when everything began in time. The cosmic background map showed a smooth start. A uniform beginning, but the universe now isn't smooth. It's full of clusters, filaments, huge, empty voids. So the question was how we got from that even whisper to this intricate structure. That needed a different map, not just where galaxies are on the sky, but how far away they are in space. A 3-dimensional atlas. In the 1980s, a team at the Harvard-Smithsonian Center started a big project. They used a relatively small telescope, but with a clear purpose. Night after night, they measured redshifts for thousands of galaxies. Redshift is that stretch in the light that tells you how fast a galaxy is moving away. And because the universe expands uniformly, that speed gives you distance. Measure the redshift, you know how far the galaxy is. They plotted each galaxy as a point in a vast 3-dimensional volume. The first slices came out in 1986, and what they showed was breathtaking. The galaxies weren't random like spilled salt. They formed patterns. Immense patterns. The most stunning was a structure they called the CF, a Great Wall, a colossal filament of galaxies, a sheet hundreds of millions of light years long. Like a continent in space, and around it, surrounding it, were these regions of shocking emptiness, voids, enormous bubbles of near-nothingness, hundreds of millions of light years across. This was the first true map of the large-scale structure. It showed a cosmos built like a sponge or a web, dense knots and connecting filaments of galaxies with great dark bubbles in between. It revolutionized cosmology overnight. It proved the distribution of matter wasn't simple or random. It was organized on the grandest scales. Theories of galaxy formation, which had focused on individual islands, now had to explain an entire cosmic metropolis. How did gravity pull matter into these vast walls and leave such empty deserts? The map was a puzzle of magnificent scale. It showed our local universe, out to hundreds of millions of light years, was just one neighborhood in a single, complex structure. And it raised the next question: was the Great Wall the biggest thing, or just one thread in an even larger tapestry? Penzias and Wilson heard a hiss. A perfect, even whisper, but if the beginning was perfectly smooth, then the present should be smooth too, and it's not. Our universe is full of lumps. So the whisper must have had a texture, a faint grain. The COBE satellite went up in 1989 to listen for that grain. It looked at the cosmic background with instruments much more sensitive than anything on the ground. It collected data for years. The first map it made showed exactly what you'd expect, a stunningly uniform sea, but they kept looking. They subtracted that smooth, dominant signal. And in 1992, they announced what they found: the primordial fingerprints, a map of the sky painted in the faintest temperature variations, tiny ripples. Hot spots and cold spots differing by just 1 part in 100,000, millionths of a degree. To the eye, it was a mottled oval, a quiet pattern of blobs. But to a cosmologist, it was seismic. Those tiny fluctuations were the seeds, the gravitational anchors, slightly denser patches where matter had begun to clump. Over billions of years, gravity worked on those specks, pulling more matter toward them. The dense spots grew into clusters of galaxies. The emptier regions became the vast cosmic voids. Every galaxy, every structure we see was written into that faint, speckled pattern. COBE map was the origin story. It connected the smooth fireball of the Big Bang directly to the sponge-like cosmic web we live in. It confirmed a prediction. For a structured universe to exist, its blueprint had to be imprinted at the very beginning. This wasn't just a map of temperature. It was a map of destiny, a genetic code for everything. In 1995, astronomers pointed the Hubble Space Telescope at a patch of sky. It was a decision. A controversial one. They chose a spot near the Big Dipper that looked empty, no bright stars, no known galaxies, just darkness. For 10 days, Hubble stared at that one point, collecting every photon of light it could, and the result wasn't a picture of nothing. It was a window, the Hubble Deep Field, and what it showed was staggering. In that tiny patch of sky, no bigger than a grain of sand held at arm's length, they found over 3,000 galaxies, not stars, entire galaxies, each one a smudged island of billions of suns. Some were majestic spirals, others were red blobs, elliptical galaxies, and many were small and blue, irregular fragments, galaxies caught in their youth forming stars. This was a map of space, but it was also a map of time, because light takes time to travel. The farther away the object, the further back in time we see it. The deep field was like a core sample, drilled into the history of the cosmos. The faintest, reddest smudges were galaxies seen when the universe was very young. This one image changed how we see our place. It gave us proof, visual proof of galaxy evolution. You could see the progression in a single frame, the young, chaotic building blocks in the back, the mature, structured systems closer to the front. It turned cosmology into a historical science. We could compare galaxies from different epochs, like flipping through a family album of the universe. But maybe the deepest impact was on scale. If 3,000 galaxies fit in a random speck of sky, then the total number in the observable universe, it's in the hundreds of billions. The universe was vaster than we imagined, and yet the deep field also made it feel connected. Every one of those smudges was a story, gravity pulling gas into stars. Generations of suns living and dying, potential worlds. By staring into a void, Hubble showed us we're surrounded by an ocean of islands, each with its own past. its own narrative. To understand the universe, you sometimes have to look at nothing and see everything. The Hubble Deep Field gave us a look into the past. But it was a narrow look. To really understand the universe's structure, we needed more than a core sample. We needed to map the whole forest. That meant a new kind of survey. So in the late 90s, two big projects started: the 2-degree field galaxy redshift survey and the Sloan Digital Sky Survey. Their goal was to build a 3-dimensional atlas of the cosmos. On a scale no one had tried before, they weren't just taking pictures, they used these fiber optic spectrographs, ingenious devices. They could capture the light from hundreds of galaxies all at once. Each fiber, positioned by a robot, would take the light from one faint smudge. That light got split into a spectrum. It showed the galaxy's chemical fingerprint. And crucially, its redshift, its velocity moving away from us, and from that, its distance. Over years, these surveys measured redshifts, not thousands. Millions. They built a point cloud of staggering size. Each point was a galaxy. And when you rendered those points in 3 dimensions, using the measured distances, the universe showed its true face. The visualizations are breathtaking. You fly through a cosmos built like a vast, delicate sponge. Galaxies aren't scattered randomly. They're woven into a colossal web. Dense knots where thousands of galaxies swarm in clusters. Long, thin filaments connecting those knots, like bridges of light spanning hundreds of millions of light years. And between the threads, the shocking, empty vastness of cosmic voids, bubbles of near-nothingness, so large that light takes hundreds of millions of years to cross them. This was the cosmic web, no longer a theoretical sketch, but a quantified, navigable landscape. The revolution was in the statistics. With a map of millions of galaxies, you could move from describing single structures to measuring the universe's fundamental properties. You could see the imprint of sound waves from the early universe, frozen into the distribution of galaxies, a pattern called baryon acoustic oscillations. That imprint became a standard ruler. It let cosmologists measure how the expansion of the universe has changed over billions of years. The maps also showed how dark matter, the invisible scaffolding, must be distributed to sculpt the web we see. The sheer number of data points turned speculation into precision. These surveys didn't just show us what the large-scale structure looks like. They told us how much dark energy is pushing it apart, how much dark matter holds it together, and how the initial seeds seen by COBE grew into this magnificent, tangled metropolis. The universe became a place you could not only see but measure. And every measurement was an answer and a deeper mystery. COBE gave us the first look at those seeds, but it was blurry, like a whisper from another room. To really hear the story, you needed every syllable. That was the job for the Wilkinson Microwave Anisotropy Probe, WMAP. It launched in 2001, and for 9 years it stared at the cosmic microwave background. Not just listening, mapping, with a sensitivity and a resolution that was way beyond anything before. What it gave us was a full sky portrait of the infant universe. A map of the faintest temperature differences in exquisite detail. It looked like a cosmic egg, speckled with hot and cold spots, and each speckle, each variation in that pattern was a message. A data point from when the universe was only 380,000 years old. This map wasn't just a picture, it was a ledger. By measuring the precise size and distribution of those temperature fluctuations, scientists could do a kind of accounting. They could calculate the universe's geometry, whether it was flat or curved like a saddle or closed like a sphere. WMAP data said it was flat, to within a tiny margin of error, which confirmed a key prediction of cosmic inflation. The map also let them pin down the universe's age with stunning precision: 1377 billion years old. Not a rough estimate, a number known to within a fraction of a percent, and most importantly, the map revealed the recipe. the exact ingredients of everything. It established the standard model of cosmology, a universe made of just 5% ordinary matter, the stuff of stars and planets, and us, 27% dark matter. The invisible glue holding galaxies together, and a dominant 68% dark energy, the mysterious force accelerating the expansion. This one detailed map turned cosmology from something speculative into a precise mathematical science. It gave a definitive, data-rich portrait that became the benchmark. Every theory about the universe's birth and evolution now had to answer to the patterns in WMAP map. It was the ultimate birth certificate, and it told us with sobering clarity that the world we know is just a tiny fraction of a reality governed by forces we are only beginning to name. The universe isn't quiet. It has this serene beauty, all the stars and nebulae, but there's another layer underneath that, a layer of pure violence. You can't see it with your eyes. You can't see it with a regular telescope. To see it, you need a different kind of sight. You need to see in energy, torrents of energy, not in colors of light. So that was the point of the Fermi telescope, the Fermi Gamma Ray Space Telescope. It launched in 2008. Its job was to map the whole sky in gamma rays. Gamma rays are the highest energy light there is, and the map it made is a map of extremes. It's a portrait of cosmic fury. Where we see the steady glow of stars, Fermi's map shows these searing beacons. Titanic explosions, it shows these colossal jets. They're screaming out from the hearts of distant galaxies, from supermassive black holes, and it finds pulsars. Spinning neutron stars like lighthouses, beaming out intense radiation, and then it catches the flashes, the brief, staggering flashes of gamma-ray bursts. They're the most powerful explosions since the Big Bang. They probably mark the birth of a black hole, or the collision of dense stellar corpses. This constant surveillance, watching the whole sky, it changed high-energy astronomy. Before Fermi, we just caught glimpses. Now we have a live monitor, a monitor on the most energetic processes in the cosmos. The map showed us whole populations of objects we never knew were there. It showed us the Milky Way differently, not just as a band of stars, but as this fog, a diffuse gamma-ray glow. That's the afterglow from cosmic rays. Ultra-fast atomic particles slamming into interstellar gas. So this map forces a shift in perspective. The peaceful night sky is an illusion. It's a calm surface, but underneath is an ocean of unimaginable power. Fermi's map pulls back that curtain. It shows us a universe where the rules of physics are pushed to the limit. Where gravity and magnetism create these engines of pure energy, and it's a reminder, to understand the cosmos, you have to listen to all its voices. Especially the loudest ones. For a long time, the map we had of planets was a lonely map. It was just our solar system, a star with 8 worlds, and then a huge, empty space. And the question was, were we just a cosmic accident, something rare? The answer didn't come from looking at a lot of stars. It came from staring at one small piece of the sky. In 2009, the Kepler Space Telescope did that. It fixed its gaze on a single field, in the constellations Cygnus and Lyra. It watched over 150,000 stars there. Continuously for 4 years, its method was simple. It looked for the tiny, periodic dimming of a star's light, that telltale shadow of a planet crossing its face. A transit. This wasn't about finding one special world. It was about taking a census. Kepler's mission was to answer one big question statistically. How common are planets like Earth in our galaxy? The data that came back painted a new map, a map not of locations but of probabilities, a demographic chart of other worlds. Kepler discovered over 600 confirmed exoplanets. Thousands more candidates. The numbers told the story. Planets are not rare, they are everywhere. They actually outnumber the stars in the Milky Way. The galaxy isn't a dark sea with a few scattered islands. It's an archipelago teeming with worlds. Kepler's statistical map showed the architecture of planetary systems. It showed that small, rocky planets like Earth, Venus, Mars are the most common type in the cosmos, and it found that a significant fraction of stars have planets orbiting in their habitable zone. That region where temperatures could allow liquid water on a rocky surface. This changed the perspective. Before Kepler, finding an exoplanet was like discovering a strange animal in a remote jungle. A fascinating oddity. After Kepler, we understood we were walking through a thriving ecosystem. The science shifted from the discovery of curiosities to the study of populations. We could ask new questions. What's the typical spacing of planets? How do solar systems form and evolve? What does the most common kind of world in the galaxy look like? Kepler's map gave us the context. It showed our own solar system is just one arrangement among a staggering diversity of possibilities. Some stars have systems of planets orbiting closer than Mercury is to our Sun. Others have worlds with years lasting only a few days. The galaxy is a tapestry of orbital patterns. This statistical portrait did more than fill in blank spaces. It reshaped the ultimate question about life. If rocky planets in temperate zones are common, then the potential for life to arise isn't confined to one fragile experiment on Earth. It's woven into the fundamental fabric of the galaxy. The universe, according to Kepler's map, is built to make worlds, and on countless worlds the story might just be beginning. The Planck satellite went up in 2009. It was the next big step after WMAP. Its job was to look at the cosmic microwave background, but with much sharper eyes. It watched that faint glow for more than 4 years. It wasn't just measuring temperature. It was looking for something finer, the polarization. So the afterglow isn't just light. It's light with an orientation, a kind of gentle swirl imprinted on it. That polarization is like a map inside the map, a whisper inside the whisper. It holds a signature from the very first instant. The patterns in that polarized light are like fossil ripples. They come from the primordial soup. They tell us about gravitational waves that might have shaken the baby universe. This was during a time of hyper-expansion called inflation. They also give us clues about the particles that filled that early fireball, what dark matter might be. The mass of neutrinos, those ghost particles that pass through everything. Planck's final maps came out in 2013. They are a masterpiece of precision. They sharpened every cosmological number to a razor's edge, the age of the universe, its expansion rate, how much dark matter and dark energy there is. All of it known with a confidence that felt almost absolute. This map gave the strongest evidence we have for the inflationary Big Bang model. It pushed our understanding back to a tiny, almost impossible fraction of a second after the beginning. We weren't just looking at a baby picture anymore. We were reading its genetic code, seeing the forces that shaped its first breath. But then, with all that precision, new puzzles showed up. Subtle anomalies in the data, things that don't quite fit the simplest story, hints that our cosmic blueprint, elegant as it is, might still be missing something. Planck's map gave us the universe's genetic code, but our own home, the Milky Way, its story was always in pieces. We could see the stars, but not their journeys. For that, you need more than a snapshot. You need a time-lapse. You need to know where a star is exactly and how it's moving precisely. And you need to track 1 billion of them. That's the Gaia mission, launched in 2013 by the European Space Agency. This observatory isn't taking pictures. It's a census taker. Its goal is to make the largest, most precise 3-dimensional map of our galaxy. It measures the positions, the distances, the motions of over 1 billion stars. To understand that precision from Earth, Gaia could measure the diameter of a human hair on the moon. That detail, applied to 1 billion points of light, it changes everything. This isn't just a map of where things are. It's a map of where they've been, where they're going. A dynamic movie of the Milky Way's evolution. With this data, astronomers are becoming galactic archaeologists. They can rewind the stellar motions, trace families of stars that move together, showing their common origin. And here, the map gets revolutionary. Gaia's data has revealed faint rivers of stars flowing through the galactic halo, stellar streams. They're the remnants of smaller dwarf galaxies that came too close. The Milky Way's gravity stretched them out, cannibalized them over billions of years. These ghostly trails are the only evidence left. We are mapping the fossil record of our galaxy's growth. It wasn't born in isolation. It was built piece by piece through ancient mergers. Gaia also measures the subtle wobble of stars, revealing unseen planets. It charts the galaxy's rotation precisely, helping us weigh the invisible dark matter halo that holds it together. Every data release from Gaia is like turning on new lights in a vast, dark museum. We're not just looking at a beautiful spiral anymore. We're reading its autobiography, written in the precise trajectories of a billion suns. We're watching our galaxy breathe and move and remember its past. A black hole is where gravity wins. For 100 years, it was just math in Einstein's equations, a point of infinite density, a place where gravity gets so strong that light can't get out. We saw what they did, stars orbiting something invisible, huge jets of energy coming from the centers of galaxies, but the thing itself was always hidden. Behind the event horizon, the point of no return. How do you map a shadow? How do you photograph an absence? The answer was to make a telescope as big as Earth. The Event Horizon Telescope collaboration didn't build one dish. They connected radio observatories around the world, from the deserts in Chile to the mountains in Hawaii, from the South Pole to Spain. They synchronized them with atomic clocks, and that created a virtual instrument the size of the planet. Its resolution was sharp enough to read a newspaper in New York from a cafe in Paris. Their target was the supermassive black hole in the galaxy Messier 87, a behemoth 6.5 billion times the mass of our Sun. For several days in April of 2017, every telescope in the array stared at that one point. They collected waves, not light waves, but radio waves from superheated gas swirling almost at light speed just outside the event horizon. The data was immense. Too much to send over the internet. They stored it on hundreds of hard drives and flew them to processing centers. For 2 years, teams worked to calibrate and combine that ocean of data, to build algorithms that could reconstruct an image from sparse signals. Then, in April of 2019, they showed it, a map of the unseeable. A fiery, lopsided ring of orange and yellow around a dark central shadow. That ring wasn't the event horizon itself. It was light from the accretion disk, bent and lensed by the black hole's monstrous gravity. The dark center was the shadow of the event horizon set against that bright ring. It was a direct image of gravity shaping space-time. This map did more than confirm black holes exist. We already strongly believed that. It gave us a precise lab to test Einstein's general relativity in the most extreme place possible. The size and shape of that shadow matched the predictions for a spinning black hole of that mass. A triumphant validation of a century-old theory, but the image also opened new windows. The brightness asymmetry in the ring told us which way the black hole was spinning and how the material around it was moving. It gave us a direct view into the chaotic physics of accretion, the process that feeds these cosmic monsters and powers those huge jets. The map turned the black hole from a theoretical idea into a tangible, measurable object. An object with a structure we can now study. With that first shadow mapped, the Event Horizon Telescope has already looked toward our own galactic center. To Sagittarius, a star, they unveiled its shadow in 2022. Each new image adds detail to our atlas of the extreme. They're teaching us not just about destruction, but about creation. about how the most violent objects in the universe can also be the engines that shape galaxies. We're not just calculating the darkness anymore, we're starting to see its face. Space seems quiet, but that's an illusion. Behind the stars, it's all violence. We saw hints of that through Fermi, through gamma rays. To really map the furnace, though, you need to see the heat. The glow from matter heated to millions of degrees, that's X-rays, and for that, a new mapmaker arrived, the E-Rosetta telescope. It launched in 2019 on the Spectre RG spacecraft. Its goal was one full, sensitive X-ray survey of the whole sky. Its first scan finished in 2020. That map isn't a picture, it's a revelation, a census of the hot universe. Where optical surveys show calm starlight, E-Rosetta shows a cosmos on fire. Millions of supermassive black holes in a feeding frenzy, their disks glowing as they eat. Vast clouds of superheated gas filling galaxy clusters, the largest structures we know, and the delicate, expanding shells of supernova remnants, the scattered ashes of dead stars. The revolution is in volume, in sensitivity. Old X-ray telescopes studied one object, one patch at a time. E-Rosetta has 7 nested mirror modules. It performs a continuous, sweeping scan. It's not looking for specific targets, it's listening to the whole X-ray symphony at once. So for the first time, we get a complete demographic survey of the high-energy cosmos. We can ask questions with statistical power. How many active black holes are there? How do they evolve over time? How is the superheated gas distributed? That gas holds most of the ordinary matter in the universe, but maybe its deepest contribution is to the map of the cosmic web. Galaxy clusters aren't random. They trace the densest knots in the dark matter scaffolding. The hot gas in these clusters shines in X-rays, so E-Rosetta finds them with incredible efficiency, even far away. By mapping the positions and masses of hundreds of thousands of clusters, it traces the large-scale structure of the universe with new fidelity. This is a new kind of ruler. The growth of these massive clusters over billions of years is sensitive to the push of dark energy and the pull of gravity. By counting clusters across cosmic time, E-Rosetta map gives one of the tightest constraints yet on dark energy. Is it constant? Does it change? The answer is written in the distribution of these celestial furnaces. This X-ray map does more than catalog violence. It uses that violence as a tool. The searing heat of black holes and cluster gas becomes a backlight. It illuminates the invisible architecture of everything. It turns the most energetic processes into precise probes of the universe's deepest mysteries. We're not just observers of the cosmic fire anymore. We're using its light to measure the shape of the house that contains it. The deepest map we have arrived in the summer of 2022. It wasn't a map of distances. It wasn't a catalogue of galaxies. It was a window into a lost epoch. The James Webb Space Telescope pointed its golden eye at a galaxy cluster, SMACS 0723. That cluster is so massive it warps spacetime. It acts as a gravitational lens. It magnifies the faint light from galaxies far behind it. It stretches and bends their images into luminous arcs. What Webb saw there wasn't just a deeper version of Hubble's fields. It was a different universe, a universe in its infancy. The galaxies in this map aren't majestic spirals. They're small, they're chaotic, they're brilliant. Blazing with the light of their first generations of stars, this image is a map of cosmic dawn, a portrait of the universe when it was only a few 100 million years old. For the first time, we're seeing the building blocks of everything, the galactic seeds, the seeds that would one day grow into giants like our Milky Way. The shock wasn't just seeing them, it was seeing so many of them and seeing them so early. The models predicted the first galaxies would be small and dim. They'd slowly coalesce over time. Webb's map shows a sky already crowded with bright, developed galaxies, far earlier than anyone thought possible. some of these infant systems show surprising structure. Disks and clumps, that suggests they assembled with breathtaking speed after the Big Bang. This map is forcing a rewrite. Our understanding of how galaxies form is being questioned. How quickly gravity pulled the first wisps of gas into suns, that's being questioned. The cosmic dawn may have been a sudden, brilliant sunrise, not a slow, gradual brightening. Beyond reshaping galaxy formation, this map probes a fundamental transition, the epoch of reionization. After the cosmic microwave background faded, the universe was dark. It was filled with a fog of neutral hydrogen gas. Then the first stars and galaxies switched on. Their intense ultraviolet radiation began to strip electrons from that hydrogen fog, reionizing it, making the universe transparent to light once more. Webb's deep fields are our first direct look at the sources of that transformative light. By studying the spectra of these ancient galaxies, astronomers can measure how their radiation contributed to clearing the cosmic fog. This map isn't just showing us baby pictures. It's documenting the moment the universe turned on the lights for good. Every point of light in Webb's deep field is a message from a time when the cosmos was new. It pushes the observable boundary back to within a stone's throw of the beginning itself, and with each new observation, this map becomes more detailed. It reveals an early universe that is stranger, more active, more wondrous than our best theories dared to predict. We're no longer just inferring our origins from fossils. We're starting to watch the birth of the cosmic web in real time. Across billions of years, the story of everything is being revised, one brilliant, ancient smudge at a time. This legacy of mapping is a conversation that goes back centuries. None of these 25 charts just appeared. They were answers to questions that came from the map before. Tycho Brahe's obsessive star positions gave a data set so precise it broke the old idea of circular orbits. That forced Kepler to find the ellipses. Then the photographic plates from the Carte du Ciel, they gave a permanent record. An objective one that let astronomers compare across time, and that's how they discovered what galaxies really are, and the faint hiss of the cosmic microwave background that was just noise. Until the Big Bang theory gave it a story, a meaning, and it became the first portrait of the universe. That's the hidden engine, how astronomy moves forward. It's a cycle. A map makes a claim about the cosmos and its success, its use that eventually shows its flaws, shows its boundaries. Those imperfections become the coordinates for the next survey. The process is relentless. Each map is a provisional truth, the best explanation you can have with the tools and the vision of the time. It stands until a new instrument, a new insight, draws a better one. The Almagest, with its Earth-centered universe, was a magnificent predictive machine for over 1,000 years. It wasn't wrong because it failed. It was wrong because a new map came along. One built with better data, a sun-centered geometry. It just succeeded more elegantly. Our current standard model of cosmology, with dark energy and dark matter, that's written in the patterns of the Planck satellite's map. That map is our current masterpiece, but it has anomalies too, subtle ones, whispers that don't quite fit. Those aren't failures, they're invitations. They're the questions for the next cartographers, the ones using telescopes we haven't built yet. That's what they'll answer. The journey isn't toward a final atlas of everything. That may never exist. The journey is the refinement, the slow, collective work of turning a blurry sketch into something sharper, something deeper, more wondrous. We're all part of that project. Every time you look up and wonder, you're adding a little more detail to the map. From Babylonian tablets to the data coming from a space telescope, all these maps are connected. They're landmarks of human curiosity. Every chart, every survey, every speckled image, it's a moment we stopped and looked up and tried to understand the scale of things. It's a story about ingenuity, about building better tools to ask better questions. But it's also a story about perspective. Every one of these maps did the same basic thing. It shifted where we were looking from. It corrected our path. It showed us that what we thought was central might be off to the side, that what looked empty was actually full, and that the edges of what we can know are always there to be moved. These aren't just scientific records, they're chapters in a kind of autobiography, the story of us figuring out where we are. We went from seeing the sky as a dome of lights to knowing we're on a rock, orbiting a normal star in the outskirts of a spiral galaxy, which is just one part of a cosmic web so large it's hard to grasp. That change didn't happen all at once. It happened line by line, dot by dot, photon by photon over centuries, each map built on the one before, using what worked and what was wrong as a guide for the next look into the dark. And that look is still going. The next cartographers are already working. The Vera Rubin Observatory will start a 10-year scan of the whole southern sky, making the biggest movie of the universe, watching for the subtle movement of dark matter. The Nancy Grace Roman Space Telescope will look across cosmic time with a view 100 times wider than Hubble's, mapping dark energy with a new kind of precision. These aren't just bigger telescopes, they're new kinds of eyes. They'll draw maps in dimensions we're just starting to think about, tracing the flow of time and where the invisible things are. The data is flowing right now, and somewhere in all those numbers, the next chart, the one that changes everything, is waiting. It has a secret we can't picture yet. Maybe a flaw in gravity, a new piece of the cosmos, maybe even a hint of something outside our reality. The map is never done. It's a living thing, a conversation between the universe and anyone patient enough to listen. And the universe, as these 25 maps show, always has more to say. The story of these maps sits for anyone who's ever looked up and wondered. That curiosity is what drives the next discovery. What comes next on a map? It could be dark matter, a glowing web we finally see, or the atmosphere of a distant world and a sign of life there, or maybe even other universes, their imprint pressed against the edge of ours. Those possibilities, they start with the questions we ask, and the next cartographer, what will they find? That's something to think about. Our exploration of the cosmos, it's shared. Your view is part of it, so keep looking up. When you trace a constellation or see a planet's glow, you're continuing that old work. You're drawing your own line on the map.